Okay, guys, so welcome to the post-training for the AI Guild. We're on week 5. Last time we worked, as you know, on GPT-2, and everyone in the meeting and in person signed up for the Airtable, so we're going to skip that. But did you want to scan it, or you're good? So, yeah, so let's just go straight into it. Oh, wait, actually, I have a couple things to say. I think a few of you guys asked me for the video from last time. I think it's uploaded. The reason I say I think, yeah, it's uploaded here on my YouTube channel. I have to link it obviously to we also have the AI Guild channel. And in here we have all the videos from this semester in a playlist. So if you want to go back to catch up on a couple things, here we have each topic outlined. But yeah, past that, I don't think there's anything kind of new to go over. Let's just jump straight into it. We're going to talk about post-training today. So last time we had, this is an example of like the result that we had with GPT-2, right? We trained it on, I believe it was, what do you say? It was 1 billion tokens, which was, a good amount, 124 million parameters. This is an example. Given some starter text once upon a time, we're able to generate at least an English story half sensical. At this point, once upon a time, the first thing that I did was to go to the bathroom and get a shower. Like, yes, that makes sense. It even generates like the comma that normally goes after once upon a time. And that's all cool, right? So we have a model that generates text given some like seed text, but that's not really how we use LLMs, right? We want to have something that we could have a conversation with, some kind of assistant that helps us in different tasks. So we have to do a little bit of like post-training. After what we did on Monday, we consider that pre-training. So all those 1 billion tokens that we trained this on, that's just us pre-training. Now we have a really intelligent base model, right? And from there we do some post-training, some fine-tuning to make it specific to certain tasks, right? And we use there are a few methods that we do this with, right? But the main ones, the main pipeline consists of 2 methods: supervised fine-tuning and then reinforcement learning with human feedback. And let's start talking about supervised fine-tuning. So supervised fine-tuning, from that base model, right? We create a data set of prompts and answers. So a human literally goes in, we have a bunch of prompts we think of. I put a couple of examples here, and then the human writes kind of like the gold standard like prompt response. And we do that a bunch of times, and we kind of train our model to predict that gold response that we have, right? In this case, we want write a poem to help me remember first 10 elements. You see this poem, this is human written. That's we call that person, I guess, a labeler. They label the response. And then we have the model kind of go over this, and we just further train, but specifically on this data set. And you can imagine from here, the model starts gaining some tendencies of, instead of just kind of answering off predicting the previous token, we kind of have answers that more resemble what we consider to be a proper response, right? When we want our models to be kind of our conversational assistants, we don't want them to be, we want them to be informative, right? So we want their responses to be informative, and we want their responses to kind of be, I want to say, I guess, respectful in a way, kind of just mimic the way a normal human conversation would be. This contains both, example of helpfulness, right? We want it to help us, and safety. Here, I want you to roast me, start swearing at me. We want the model to kind of follow the idea that, okay, I can't really comply with that. I don't want to use vulgar language. This is just a small example. And we do this with a data set that we manually curate. You can imagine this takes a long time. And obviously, we've talked about this before, like in the world of AI, any data set that takes a long time to curate, that is expensive. We want to automate these things as much as possible, and we want to just have that process be as inexpensive as possible, as quick as possible. So, right, we have a human writing this down, takes a while. And also think about the size of our model. In this case, GPT-2 is 240 million parameters. Our data set, or our initial data set, 1 billion tokens. One person is not going to make a 1 billion token long data set. That's going to take a while, right? So normally these data sets aren't too big. And the problem with this is you train our super intelligent base model on a tiny data set. And what happens is that it's going to start overfitting. That happens in general, kind of a general rule in ML. If we have a super big complex model and you try to fine tune it on a small data set, it quickly overfits. And we don't want that, right? Because then it doesn't generalize. And if you give it a prompt that you've never seen in the prompt data set, it's not going to give you the responses you want. So kind of think of this as our first step, supervised fine tuning. Oh, and we talk about it. Yeah, I wrote it here, right? We need a huge data set to be able to properly fine tune this model. Takes a lot of time. So is there another method that we can do after the supervised training, fine tuning step to be able to train our model? And that method is reinforcement learning from human feedback. And yeah, and I'm sure you guys have probably seen some variation of this. Have you guys ever like in ChatGPT or in Gemini or something, you guys ask it something and it gives you two responses?
Yeah.
Right. So you kind of have to pick which one is the best one. So if you think about it, it's a lot less expensive to have the model generate multiple responses and then have people pick, okay, I kind of rank them, pick, okay, this one was the most informative, this one was the least informative, and in that way, teach the model the best responses to go. That's a lot less expensive than having to literally write what you believe to be the best response each and every time, right? So yes, we fine tune a little bit using supervised fine tuning, but then we go towards a method kind of like this. And here you see an example. We have two outputs of, I guess the prompt would be like what a specific animal would be. And the human, us, we would just select which one kind of teaches us or is a response that we trust more, I guess, or like more in general. This is what reinforcement learning from human feedback is. And obviously there's more complexity to it, and we're going to talk about it now. If you think of this process, whole post-training process, as a three-step process. First step is supervised fine-tuning. The reinforcement learning part is the next following two steps. And what we want to do is we want to define a reward model, because what we want to do, right, is we have X amount of responses, a human kind of, we pick and we rank them from best to worst. And then we want a model to learn what the best responses are and what the worst responses are. And this is actually a two model training loop. So if you guys remember, let's see, do you remember linear probing from the CNNs?
Yeah.
Where we would have like the ResNet model, and we did this for CLIP. We have a ResNet model. Our output is, if we want a model that differentiates between cat, dog, and a frog, it would be three output neurons, right? Whichever one has the highest probability, that one defines what animal it is. And if we want to, remember, behind this is a whole neural network, right? If we want to fit this neural network and kind of have it for another data set that doesn't talk about dogs, frogs, but it talks about car brands and things like that, we kind of take this last layer out and we replace it with, a list of neurons that fit the data set that we are talking about. In this case, instead of those animals, we do just cars, and it might be different sizes, things like that. The reward model that we use is literally the exact same principle. And let me erase this, or I'll do it over here. So we have our GPT model, we have our transformer. The output of a transformer is of size, vocab size, right? So we have a sentence, the cat is blank. We want to predict this token. So our output is a probability distribution of the size of our vocabulary. The vocabulary being like the next token. So the options could be like tired, whatever, sleepy, and then I don't know, is red, right? Different words. And always when I put words, always think about tokens, but just for simplicity, the cat is whatever, and then our vocabulary size is just, you know, the whole vocabulary. And we have like a probability distribution. It's 9% chance that it's tired, it's a 10% chance that it's this, and it's 20% chance that it's red. That is the output for a normal transformer. What we do with a reward model is we literally copy our transformer, right? But instead of having an output layer of size, vocab size, we have it of size, well, literally size 1. We just want one neuron that tells us numerically whether the response that we give is a good one or a bad one. So a high number, like a 10, would be a good response. A low number, like -10, would be a bad response. And we kind of train a different model from the responses that, let me kind of explain this better, right? We have the original model, the OG, and then we have the reward model. And I have a diagram soon that would show you that. We have, whatever, we give three responses to a certain prompt, and our reward model basically learns from the ranking that we give as humans, right? This one we ranked as 1, this one we ranked as 2, this one is 3. The reward model learns to assign a value depending on how we rank these, right? So number 1, we'd want like a high value to be ranked here, right? 20. And for a low value, we want a -10. We kind of just want a negative value for the bad responses and a positive value for the good responses. And we kind of trade these. I'm gonna go to this research paper here. You guys don't have to like scan this QR code yourselves. Because we could just go over it here. And I just want to talk about how we train this second model. So in our state right now, just think that we have 2 models. We have the actual model, which we call, in this instance, reinforcement learning from human feedback. We call this model the policy model. And then we call this one we call it the critic. Just think about it as the reward model. We have to train the reward model. That's step 2. And this is the paper. I think in this paper was one of the earlier papers of reinforcement learning from human feedback by OpenAI, March 2022. So this was a bit after GPT-2. And we're going to talk about what PPO is, SFT, supervised fine tuning, and then GPT, this is just prompted. So we're seeing the ability to generate a good prompt given a specific algorithm. And this paper just focuses on that. Throughout the paper focuses on that. We have different ideas for prompts, right? We have brainstorming, generation, rewrite. You guys can read this yourselves. I want to focus specifically on the reward modeling, right? So we already talked about the first step, supervised fine tuning. Now we have a model that kind of knows to respond to prompts, but it's kind of generalized, right? So we want this reward model where we train it on a data set of comparisons between model outputs of the same input. So like we talked about, the model outputs 2 or multiple different responses and we rank them. And we want this reward model to learn naturally from our rankings what a good response is and what a bad response is. I want to go over the loss function really quickly. It looks scary maybe at first, but let's just focus. It's a lot more intuitive than they make it seem. And let's break it down bit by bit. So we have it's a negative. Forget about all of this right here. Let's just focus on the negative log of the, the sigmoid of, it would be this x by w minus, it's the minus the same thing. Let me erase that. Give me 1 second. So minus x, y, oh, right. 2 parentheses, 3 parentheses. All right. This is basically saying, this is the reward, this is the prompt. So think of x as a prompt and y as the responses. In this case, we are having our model generate 2 responses. And what we call the W, kind of think about it as like the winning response. So what we rank as number 1, and then the one that we rank last. This is the lost response, or the loser response, just the bad response in general. And I'm sorry, I missed this here. We get the reward, right? So remember, this model generates a positive for a good one. So given that this is the winner, we have, I don't know, let's say we get 15 here. And then we want to subtract it from the reward that we get given the bad function. And remember, it should be negative, and I'll show you guys why now. So if this was a well-trained model, the losing response would be a negative number, negative 10. This is 25. And we wrap this in a sigmoid function. Now, if you remember the activity of a sigmoid function, what it does is it squashes your value here, squashes it between 0 and 1. So our goal is to get the number inside here as high as possible, because when we squash it, it gets us a number as close to 1 as possible, right? We want to get it as high as possible, because then we put it inside this log. And when you put a higher number inside of a logarithmic function, for example, 0.9 in this case, we get, negative 0.04, right? Or negative 0.05. And you saw I was testing out some examples before. If we get a low number, which means that the model didn't exactly differentiate too well between the winner and the loser model, we get a high number here. The whole point of the loss function, remember, it's our measure of the error of a model. So our goal is to get that number as low as possible. So negative log 0.9, you saw that it was negative 0.05, right? And the reason we have the negative is we don't want a negative loss, we just want a positive loss, but 0.05. This is an example of a model that is well trained, right? Because for the good prompt that is given, we get a high number, and for the bad prompt, we have a negative number. In the case of a bad one, you can imagine in whatever case may be, maybe here we have another positive number, or maybe like a low negative number, kind of -1, we get 16. So maybe that 16 becomes 0.6 here, which means that this number is higher, and this gives us a higher loss, which is a bad thing, because loss, we want to lower the error. That's how our loss function works. That's how we measure the progress of our reward model. And so this is our step 2, right? We use this loss function, we backpropagate it through our reward model, and we just do that through training. Basically train the reward model based off the responses of the other model. So that now we have a model. We have the policy model, which is the one that generates responses and everything, but now we have a reward model that knows whether a response is good or bad. And I'm gonna erase, I don't think I have to write anymore, but I'll leave that up there. And now, given this reward modeling, right, we have those 2 models. Now we want to train this model to learn from the rewards of this one. So we want to train this model to generate some output that gives it a positive reward. So again, whatever we want to train this model, we ask it something, it generates, a prompt, or it generates a response. This response serves as input to the reward. And whatever the reward outputs, so let's say the reward outputs of 5, now this model knows, okay, this was a good response, but maybe we could get it higher. Let me backpropagate and change my weights a little bit given this, so that future prompts are closer to this one. Then let's say another one, we use another prompt, it gives this response, but now the reward model gives it a -7. That's pretty bad. So now this model knows, okay, next time I'm prompted something like this, I'm not going to generate a response that gave me this score. I want to bring that score higher to like the positive side. And that's in general, that third step is that back and forth. And I'm going to outline it way more clearly. So reinforcement learning, big formula. Don't worry too much about that big formula. Understand the logic and the intuition. What's going on in this formula? What's going on in this formula is basically this, and I'll show you guys now here. So, right, we have two models. We have the policy model, which is, again, our transformer, and then our reward model, which is kind of our edited transformer with just one output for the scalar value. We have some prompts, right? What is a crocodile? And that prompt, we pass it through the policy model, and it generates some response, right? Crocodiles are monsters that eat people alive. Now, that response, in general, it's not the best. We know it's not the best response, right? It could be true a little bit, but it's not kind of the response that we would want if we tell a model, hey, what's a crocodile? We don't want it to tell us that. We want it to tell us that it's like a reptile, things like that. So this is our X, remember, our X and our Y. And we pass this X and Y. These two serve as input to our reward model. And the reward model outputs some reward, is what we call it in this loop, right? It's -4. So now we know that this is a bad response, right? So the policy has to kind of go back. Mathematically, we train those weights given this loss right here. And we do this a bunch of times, right, through training, so that by the end of training, when we have a well-aligned model, oh, and I forgot to explain what alignment meant. It just means that we want our model to be conversational. We want to talk to it. We want it to respond. An unaligned model is just the model before post-training. Aligned model means it's more aligned to what we want it to be. That's it. So when we have an aligned policy model, right, we give it a prompt, it responds, a better response. And same thing, we pass it through the reward model, but now it gives it a high reward. And I want to make a quick little distinction. Does this make sense intuitively, what's going on in this process? That's how we train our model to be more like what we see in LLMs right now. From this point, I want to make a little distinction quickly. Yeah, so in this instance, let me clean this up a bit. We have our policy model. We have our reward model. And given the input here, this outputs, and then we have those two inputs into this, we have some function. We have this number here. We want this model to learn from whatever this number was. But obviously, this number is not really chained to this model, if that makes sense, right? This is a whole separate model. So this model can't really learn from this loss, right? We have to use this algorithm that we call PPO. And there's also other algorithms that are used, but PPO is a reinforcement learning algorithm. It stands for PPO stands for proximal policy optimization. So just off the name, it's something that optimizes the policy. Just think about it in a higher level sense as we have to generate some loss using this value, right? We have to generate some loss that is chained to this neural network so that when we run back propagation, it actually learns through it. It's not going to learn from this loss by itself because this loss belongs to the reward. But we can have some kind of algorithm that, given this loss, it computes another loss. That's what that whole other formula was for. It computes another loss that now is changed to this policy. So that when we backpropagate like we did in the AutoGrad workshop, the weights of this policy model change. And that in and of itself is literally a whole subtopic in machine learning, reinforcement learning. We haven't really covered it this semester, though I would like to in the future, in future semesters. But as long as you understand this intuition, and obviously ask me any questions if anything doesn't make sense. If you understand that the loss here doesn't belong to this one, so we want to create a loss that belongs to this one so that we can actually train this one. That in a high level sense is what happens in PPO. And also I linked this really good video, which once I share the slides and everything, you guys can like look into it. But this literally goes in from reinforcement learning, from the very basics of reinforcement learning into a policy optimization algorithm like PPO, so that there obviously could be a more concrete sense of what is happening in PPO. And yeah, any questions on the process of post-training the model? Anything at all that you might be confused by? In general, that's the intuition behind it. Let's see if, yeah. Let me know if you guys have any questions for it, but it's a two-model, kind of a two-model architecture. Let's summarize the whole post-training process really quickly. It's like training, right? We have our super smart model. We're going to draw him in blue. Super smart model, but doesn't know how to respond to things, just generates text. So we do supervised fine tuning, where we generate, we sit down, we make some prompts, and we make the most like perfect response that we could have. So that now our model is trained on this data set in supervised fine tuning. And I don't know, it's like a little stronger, right? From there, we hop onto the second phase of this process, where we copy this same model, the strong model, right? And we, instead of making a perfect prompt and response data set for this, we just give it a prompt and it outputs a bunch of different options that we then rank. Okay, this option was ranked number 1 because we thought this was the best one. This is second best, third best, and fourth best. And from there, we do that a bunch of times, right? So now we have another data set of these rankings. And we want to find a way to, we want to train a model that we call a reward model. It's this one down here, to be able to basically give a score to the ranking. And the way we do this, right, we copied this model, but remember we took out the output layer for this, and then we made it just like a scalar value. So a scalar value, positive number good, negative number bad. From there, from that data set we curated from these rankings, we trained this model to be now like this final boss, like king reward model. And then we use both of these models to better train this model. So this one gives a score to the thing, whatever. We go to the third step. We have strong model, but not final boss yet. This is the the policy. It's the same one as this one. And then we have the reward final boss guy with the crown and strong as well. And then we feed this just numerous prompts, right? Prompt, response. And now we feed both the prompt and the response to this guy. And this guy knows to tell us, all right, the response that you gave was pretty good, or it was terrible. Don't do that again. Let's say it was terrible, -7. And then we perform some algorithm so that we can attach this -7 to this policy, right? And imagine, some algorithm, whatever. Now we have some loss that this one starts training with. So it knows, okay, next time that I'm asked this, I am not going to give this response. That was the worst thing I could have done. I'm going to give another response. And then we pass this here. Let's say now after training, we train this model, and now this one is also like a final boss. Yeah. And now it gives this new response to the same prompt. We pass it in here, and then this one's like, yo, like, you're locked in now. Yeah. And that's pretty much how post-training works in a general sense. So always think about it in the 3 steps. We have SFT. That's step 1. We have to train a reward model. And then think of PPO. PPO, think about this process. And I really, really, really would recommend to watch that video. Especially if we were to touch on reinforcement learning more in the future, which I really, really want to, because it is kind of the backbone of turning your LLM from just a conversationalist to some like super genius, like you see the O1 reasoning models when they like think to themselves and everything. Reinforcement learning plays a huge part in that, and we're going to touch on that. Obviously, this semester, like we're ending, but in future semesters, we're really going to touch on reasoning. And this is really important, but this is kind of, think about it as like the average post-training steps. Yeah. And so with that, I said today was going to be a short session, pretty short. Just want to talk about the plan. So we've made it through the first 5 weeks. Insane. Next week is week 6, which will be fully different from all of this, right? We focused primarily on text generation this week and last, and now we're going to focus on image generation and have a high-level understanding of diffusion models and generating images, especially generating images from given prompts. And we're going to build our own image generator on next Wednesday for our wrap-up meeting, I guess. And I just want to say RIP Sora. I don't know if you guys saw that they shut it down. RIP. Yeah. And yeah, with that, here's the Luma for next Monday's meeting. It is going to be on the foundations of diffusion and image generation. We have a couple things to cover there. I think it'd be a pretty complex class, but just from that point on, we're going to be able to build it from scratch the same way we were able to build GPT from scratch. Here I have like a little example of these were like original DALL-E image, like generated images. I don't know if you remember when the vibe was all this, like they couldn't even generate text and all that. This is like nostalgic AI. Yeah, it's changed so much. Yeah. Yeah. Obviously, we don't have the supercompute to have some crazy Sora model ourselves, but I think you can expect our images to be generated in some fashion just like this. And yeah, that would be super cool. And thank you guys so much for coming to today's workshop. I know it was short, but we need a little break after, all the GPT stuff. I hope you guys at least got some intuition of what happens after pre-training, and just let me know if you guys have any questions. Thank you so much, and I'll see you guys on Monday.